Welcome back to our ongoing series where we have been exploring the concept of Ethernet as the primary link layer protocol. In our previous videos, we provided an overview of its evolution and even delved into its competitors, including the token ring and FDDI. Now it's time to dive deeper into the mechanics of Ethernet. We will thoroughly examine how this widely adopted Layer 2 protocol functions in a variety of networking environments, ranging from home setups to large data centers. By delving into the inner workings of Ethernet, you will gain a comprehensive understanding of its operation and its status as the most popular protocol at the link layer. Whether you are a networking enthusiast or a professional seeking a deeper knowledge of Ethernet, this video will provide valuable insights. Get ready to uncover the intricacies of Ethernet and explore its widespread use across diverse networks. We are excited to take this deep dive with you.
Let's reflect on the origins of Ethernet, which can be traced back to its inception in Hawaii during the 1970s. We have come to understand that Ethernet operates as a broadcast network, where all computers are interconnected through a shared channel. Initially, this channel took the form of a coaxial cable, later transitioning to a central device utilizing twisted pair cables. As a broadcast network, Ethernet follows the principle that one station or computer transmits a message and all other stations receive it. This means that all stations share the same medium, and only one station can transmit information at a given time. In the event of simultaneous transmissions from two or more stations, a collision occurs, which can be detected by listening and transmitting computers. When a collision is detected, both senders promptly cease transmission and make another attempt after a random waiting period. Although the random wait may seem like a disadvantage in terms of warranty delivery, Ethernet has proven to be highly effective in practice, even at higher speeds. Another consequence of a broadcast network is that every station receives all packets or messages, regardless of their destination. This can lead to network overload and unnecessary data processing at each station. Ethernet addresses this issue by assigning a unique 48-bit address to each station. This address is included at the beginning of each frame, which is then processed by the network interface card. The card automatically discards messages that are not addressed to the particular station, reducing unnecessary data processing. Now, let's delve into the structure of an Ethernet frame to understand how Ethernet operates.
The Ethernet frame begins with a preamble which consists of a specific pattern of numbers, namely 1, 0, 1, 0, 1, 0, to aid in the synchronization and decoding of the rest of the frame. Following the preamble, we have the destination address field. As mentioned earlier, the receiver station checks this field to determine if the frame is intended for it. Next is the source address field, which identifies the sender station. After that, we encounter the ether type field, which consists of 16 bits and informs the networking stack about the type of payload or the data present in the upper layer, such as IPv4, IPv6, or other protocols. The structure of the frame concludes with a checksum field, which helps ensuring data integrity. Addresses play a crucial role in Ethernet frames. The destination and source addresses are 48 bits long, also known as MAC addresses, providing a vast address space. The management of this address space is carried out by the IEEE Association. Notation examples of Ethernet addresses include the use of colons, dots, and dashes, all of which are equally valid. The most common notation employs colons. Within the address field, 2 bits have special meanings. The first bit distinguishes between global and local addresses, enabling the assignment of self-assigned Ethernet addresses. The second bit indicates whether the frame is intended for a unicast or multicast transmission. Unicast denotes that only one station is the intended receiver, while multicast indicates that multiple stations should receive this Ethernet frame. Additionally, there exists a special multicast address known as broadcast address, which ensures the frame is received by all nodes on an Ethernet network. We will delve into this topic further in an upcoming session. The payload field contains the actual data carried by the frame. Some examples of payload types include IPv4 and IPv6. In summary, Ethernet functions in a manner consistent with our previous description, but with the added consideration that speeds has progressively increased over time. Now let's take a closer look at Ethernet technology as it is used in modern data centers. In these environments, optical fibers are employed, including different types such as single-mode and multimode fibers. However, they all share a common characteristic of utilizing laser light to transmit Ethernet frames at very high speeds. Present-day Ethernet networks operate at speeds ranging from 1 gigabit per second to 10 gigabit per second, all the way up to 800 gigabit per second. It is important to remember that Ethernet began with a modest speed of only 10 megabit per second, which was more than 1,000 times slower. Ethernet in home networks primarily uses copper cables due to their ease of handling. The speeds commonly found in home networks are either 100 megabits or more frequently today up to 1 gigabit per second. It is also common to have a wireless Ethernet extension known as Wi-Fi to provide connectivity throughout the home. In a home network, switches are also used. These intelligent devices learn which port each computer is connected to, allowing them to forward frames only through the ports where the correct receivers are located. Switches achieve this by examining the Ethernet frames and extracting the source address as we explained previously. Ethernet has a limited payload size of 1,500 bytes or octets. While some implementations utilize jumbo frames with 9,000 bytes, this practice is not widespread. The addressing scheme remains at 48 bits, and Ethernet continues to be a widely adopted technology, commonly used in most switches. To summarize, we have explored Ethernet as a broadcast network where computers share a common channel, with its origins dating back to the 1970s in Hawaii. Ethernet utilizes fiber or copper twisted pair cables and a central device for transmission, with collisions occurring when multiple stations transmit simultaneously. Despite the lack of guaranteed delivery, Ethernet has proven highly effective and operates at high speeds. To prevent network overload, each station possesses a unique 48-bit MAC address, with frames discarded if the destination address does not match. The Ethernet frame structure includes a preamble, destination and source MAC address, Ethertype and checksum. Ethernet has evolved to support faster speeds in modern data centers and home networks using either copper and fiber connections. Switches play a crucial role in forwarding frames to the appropriate receivers. Ethernet retains its use of 48-bit addresses and remains a widely adopted technology. Thank you for joining us, and we look forward to seeing you in the coming videos where we will delve into virtual LANs, also known as VLANs.